doing hydrolysis calculations, so we can turn to page 107. Now, when you guys take a look at this question, now here's the problem that you guys are going to come across, is that when we break down every single concept in acid base in its own distinct little sort of time slot and not mix it with anything else, it sounds and feels very straightforward. But it gets more complicated as I start pulling things in together. So for example, if I take a look here, it says, what is the pH of a 0.15 molar solution of KCH3COO? And you're like, oh, well, we're in the hydrolysis section, so we're going to need to calculate that. But in this case, let me ask you this question. So you don't have to write this down. But
Bless you.
What if I said, what is the pH of a 0.15 molar of HCl versus what is the pH of a 0.15 molar of HF? What is the pH of a 0.15 molar of NaOH? And what is the pH of a 0.15 molar of NH3? Now, when you take a look at this, one of the things that I want you, and then so now we have what is the pH of a 0.15 molar of NaCH3COO. So notice all of these questions look exactly the same, right? So over here, if you take a look, they're all starting with what is the pH of. So the only thing that is now changing or is different is the type of substance that I have over here. And so this is why I always ask, what are we working with first? And the reason is based on what we're working with, you're going to be approaching the solution differently. One thing you're realizing is the math all kind of looks the same. But depending on what you're working with, the kind of math you apply is going to be slightly different. So you take a look at this and you're like, okay, I know, then that's good. But if you're looking at this going, I don't even know where to start, then that is telling you that you probably have to go and sort of really clarify all of the different types of substances. So for the first one, if you take a look, well, what is HCl? HCl is a strong acid, so you know it's going to dissociate, and if it's dissociated 100%, then it's just a straight up negative log. However, if you have HF, is that a strong acid? No, this one's a weak acid, and so now your equation changes into that of an that of an equilibrium, and then now you have to use the equilibrium calculation, don't you? And then so the next one over here, if you take a look, well, this one's a strong base, so now you have NaOH, and it's going to break apart into Na plus OH minus, and then now you have to figure out POH and then figure out pH. And then the last one, if you take a look, you know that this is a weak base, and so now you have to generate this equation, and then now you have to figure out the OH based on equilibrium calculations, and then to figure out POH and then figure out pH, right? So in this case over here, if you identify it wrong, you will apply the wrong mathematical application, right? So I was telling my class, the previous class, is that, you know, it's easy to make a mistake and then you apply to the wrong thing. So my friend was telling me, yeah, he's a dentist, and he's heard of stories where the dentist goes and says, okay, I have to extract your tooth, and then they extract the wrong tooth. Right? Is that what happened? Right. So in this case, here, it's like, yes, they're supposed to extract the tooth, but they identify the wrong tooth. Right? So yes, if with the calculation for HCl work here, yes, but if you apply that calculation down here, it would not work, even though it's the right math. So this is why the hard part is not the math. The hard part is making sure you guys recognize what the right material is. So now when we take a look at this one, we're now dealing with KCH3COO. So therefore, the very first thing that you have to do is identify what you're working with. So the hard part here is not the math anymore. The hard part here is making sure you know what you're working with. So therefore, you ask, what are you working with? Strong acid, strong base, weak acid, weak base, or in this case now a salt. So in this case, it is now a salt. So now when you're dealing with the salt and you now have your KCH3COO, you now have to deal with, hey, which part of the salt is going to react with water? And so this is what we did up here in terms of identifying where the ions came from. So over here, we see that this came from KOH, and then this came from CH3COOH. And so in this case, the K does nothing, and that means this ion over here is what reacts with water. So now the second part over here is you guys going in and say, well, what is the equation? What's the predominant equation that is going to take place? And so in this case over here, I take CH3COO minus, and I add it to H2O, and I go and I have CH3COOH plus OH minus. You might ask the question, well, I thought it was supposed to be this. Yes, it's supposed to be that, but that's not present right now because that's not what's in the water. What is in the water is the ion that came with the salt. So now that I've done that, now the rest of this is easy because now you actually just do your K, in this case KB, and you have your 0.15, 0, 0, minus X, plus X, plus X, and then 0.15 minus X, X, and X. See. And then at this point you see that you made OH, so you're going to be using Ka or Kb. You're going to use Kb. So over here you go 1.0 times 10 to the minus 14 all over, I believe it's 1.8 times 10 to the minus 5, and you get 5.6 times 10 to the minus 10. So now you have 5.6 times 10 to the minus 10 is equal to X all squared all over 0.15 minus X. And again, just like before, we say that this is very small. And I get X is equal to 9.2 times 10 to the minus 6, which is equal to the hydroxide. And then if I find the POH, is negative log 9.2 times 10 to the minus 6. And I get 5.04. So pH is equal to 14.00 minus 5.04. And I end up with 8.96. Does this part feel comfortable to you? Yes, you've seen it a bazillion times. But it is the getting there that is hard. This part here and this part here is going to be crucial to figure out whether you're doing it right or wrong. Now, I want you to take a look at this chart and take a look at the setup. Do you see this, like, I have a certain amount here, and then this is 0, and then this is 0. Do you guys see that? where have you seen that before? And so if I go back into my notes and I go into my titration of the weak acid versus strong base, and I reach equivalence point right over here, does this chart look similar? I have a certain amount, I have 0 and 0. So essentially, this calculation for hydrolysis is what's going on during equivalence point. Because remember, you have no more of your original acid or base, so it is now the salt that is now reacting with the water, right? So what we're doing over here is we are just basically looking at bypassing all of that titration, and all we're doing is we're just adding the salt. That's it. So the hard part here is not the calculation. The hard part here is figuring out which part of the salt is going to react with water and then the subsequent equilibrium. Okay? So let's take a look at the next one. So now if you take a look at this next one over here, it says, what is the pH of 0.3 molar solution of NH4Cl? So number one over here, what am I working with? I am working with the salt. So right now you have 5 choices: strong acid, strong base, weak acid, weak base, and a salt, right? So in this case over here, it is NH4Cl. Now we do our analysis. Where does the Cl come from? HCl. Where does the NH4 come from? NH. The NH4 comes from what? It's NH3. So therefore, what do we know about HCl? What type of acid is it? It's a strong acid. That means it won't do anything. What is NH3? Weak base. Therefore, the NH4 will do something. Now that we have seen that NH4 is now going to react with water, now we can go ahead and write out the equation. And so now we have our ICE and then I go and I have my 0.30, 0, and 0. I go minus x, plus x, plus x, 0.30 minus x, and x. So what's the Ka of NH4 plus? Excellent. So it's going to be x times x all over 0.30 minus x. So the x over here is considered very small. We put it into our trusty calculator. I get x is equal to 1.3 times 10 to the minus 5 molar. Going back over here, this is the concentration of hydronium ion. So the pH is negative log of 1.3 times 10 to the minus 5. And if I was to do that, it is 4.89. Are you getting comfortable with the pattern? Okay? Good? So I'm going to throw one more curveball at you. So if you go down to the next one, again, you're like, okay, well, we're in this topic, so I know what the answer is. But again, if you were to have to take a look, what type of substance am I dealing with? And so you've got the Na, you don't have any kind of telltale hydronium ion or hydrogen ion, you don't have a telltale OH, so therefore it's a salt. Na2HPO4. Now at this point in time, you guys know that Na comes from NaOH, and HPO4 comes from H2PO4 minus, yes? So in this case, you know that this is a strong base. That means Na won't do anything. And if I take a look right now in my data booklet, and I look at my H2PO4, which is over here, we would consider it a weak acid, yes? So therefore you're like, oh, no problem. However, at this point in time, when I take a look at HPO4, is there something that kind of makes you go, it's amphiprotic? Yeah, what? How do we know? Well, remember you guys did the lab the other day, yes? And when you guys did your lab the other day, remember you had all of these. You guys remember that? And did you work with that one? Yes, you did. So in this case over here, when you now take a look, a sub-consideration you need to make is the ion amphiprotic? If that is the case now, there are two possible reactions here. So in this case, there are two possible reactions. The first reaction would be that HPO4 minus, or 2 minus, is now going to react and potentially function as an acid. So A over here is for acid, so it's now going to be PO4 3 minus plus H3O plus. Or the HPO4 minus 2 can behave like a base, so B. So in this case over here, it now becomes H2PO4 minus plus OH minus. So on the one hand, it could donate a hydrogen ion. On the other hand, it could take one. So the question is, which one is the preferred reaction? And so this is exactly like what you guys did during lab manuals. Do you remember you guys did a Ka versus Kb? Remember us talking about that last day? So now what you're going to need to do is you're going to need to go in here and you say, okay, well, what's the Ka of HPO4 acting as an acid? Can somebody please tell me? Thank you and thank you. 2.2 times 10 to the minus 13. Now for the second one, it forms a base, so it's going to be Kb. So you guys learned to convert it. You now have to have 1.0 times 10 to the power minus 14, and you're going to divide it by the Ka of the corresponding acid. So now I have to go back into my data booklet, and now I have to take a look. Oh, here is my HPO4, and this is behaving as an acid. And then do you see over here that I have my HPO4 right over here, and this one is behaving like a base. Now somebody in the other class goes, how do you know it's amphiprotic? So in general, you know it's amphiprotic if you see an H and a negative charge. However, another way of knowing this is, do you see that the HPO4 shows up on both sides? Do you see it shows up on the acid side? You see it shows up on the base side. So if you see it showing up on both sides of your data chart, that's telling you it's amphiprotic. So now I'm going to take that 6.2 times 10 to the minus 8, and I'm going to divide it. And then so in this case, I'm now going to go 1 times 10 to the power minus 14 divided by 6.2 times 10 to the minus 8. And I get 1.6 times 10 to the minus 7. So at this point in time, which one here is the preferred reaction? The acid, the A for acid, or B for base? Which one's the preferred one? It should be the base. And so this is now my preferred reaction because this one here is bigger. So now what I'm going to do is I'm going to do my ICE. And now I'm going to have 0.20, 0 and 0, minus x plus x plus x, 0.20 minus x, x and x. So now I go 1.6 times 10 to the minus 7 is equal to x times x all over 0.20 minus x. So this is very small. So 1.6 times 10 to the minus 7 times 0.2, and then we square root it, and I end up with x is equal to 1.8 times 10 to the minus 4. That's for OH minus. So POH is equal to negative log 1.8 times 10 to the minus 4. And I get 3.75. So pH is equal to 14.00 minus 3.75. And I get 10.25. So at this point in time, again, the emphasis is, was this part the hard part? No. The hard part was figuring out that you had a salt and figuring out which ion reacted with water. And then, in this case, you now had a subcategory of whether it was amphiprotic or not. So in this case over here, if you guys were to answer the question, what am I working with? You now have a strong acid, strong base, weak acid, weak base. You now have a salt, so that was your 5 choices. Now the subcategory of salt would be, is it amphiprotic? So there's 6 things you have to now consider, don't you? Okay, so it's quite extensive. So what I'm going to get you guys to do is a couple of things, is you guys can take some time to finish up your lab, and or you guys can work on worksheet number 6. It is currently 2:14. I'm going to give you guys about 20 minutes. And then afterwards, what I'm going to do is I'm going to start on buffers. Okay? So you guys want to use the time and maximize it to make sure you either